A gearbox that runs acceptably for short periods can become a reliability risk when the same load continues for hours. Small efficiency losses become heat, marginal lubrication accelerates wear, and difficult service access turns routine maintenance into extended downtime. Choosing among helical, worm, and planetary designs therefore requires more than comparing efficiency, package size, or torque density. The decision begins with the complete operating duty: output speed, continuous and peak torque, starting frequency, load variation, ambient conditions, installation envelope, and available maintenance. Motor control also matters. Variable frequency drives may reduce starting shock, but they can introduce extended low-speed operation or frequent ramping. Direct online starts, reversing, plugging, emergency stops, and braking can impose different transient loads. Helical gearboxes are commonly considered for smooth transmission, practical efficiency, compact industrial integration, and flexible inline or related configurations. They are often evaluated for conveyors, packaging machinery, and process equipment requiring controlled speed and stable torque. Their suitability still depends on ratio, service factor, mounting position, alignment, thermal conditions, lubrication, and the machine interface. A broad product family alone does not confirm that a particular configuration can withstand the required duty. Worm gearboxes can simplify machinery where a compact right-angle arrangement is valuable. That layout advantage must be balanced against the operating speed, ratio, load, temperature, and lubrication requirements. In lower-duty or space-constrained equipment, a worm unit may be a practical solution. Under sustained heavy load, however, thermal behavior and efficiency require close examination. Package size and initial cost should never conceal an insufficient thermal margin. Planetary gearboxes are frequently considered when high torque density, compact axial packaging, precision, or controlled motion is central to the application. These strengths can justify greater integration, service, and cost considerations in demanding machinery. But high torque capacity does not automatically make planetary technology the best continuous duty choice. Where a helical or another configuration meets the duty with simpler installation and maintenance, that option may create lower overall risk. 5 connected risks provide a disciplined comparison. Efficiency risk covers energy loss and operating cost. Thermal risk includes heat generation, ambient temperature, ventilation, oil condition, and mounting orientation. Load risk addresses torque peaks, shock, starts, and fatigue. Layout risk covers shaft direction, mounting, guards, and interfaces. Maintenance risk includes inspection access, spare availability, lifting requirements, and replacement time. The preferred gearbox is the one that controls the risks carrying the greatest consequence for the specific machine. That consequence varies across applications. A lightly loaded packaging conveyor does not require the same risk tolerance as a mining feeder, cement mixer, or drive capable of stopping an entire process line. Dust, high starting resistance, shock loads, chemical exposure, contamination, and washdown can make sealing, lubrication, inspection access, and thermal margin more important than a small difference in nominal efficiency. Procurement should apply the same evidence requirements to every candidate. Request the selected ratio, output speed, continuous and peak torque, thermal rating, mounting drawing, lubrication instructions, inspection evidence, maintenance intervals, and warranty terms. Confirm how spares are identified, which tools are required, and how quickly a failed drive can be removed and replaced. A detailed quotation for one technology cannot be fairly compared with a generic description of another. Reject any candidate whose known operating boundary conflicts with the machine duty, or whose supplier cannot explain that boundary. Insufficient thermal margin, excluded starting loads, an unsafe interface, or maintenance demands the plant cannot perform are valid technical reasons for rejection. For any helical, worm, or planetary gearbox, reliable continuous duty comes from verified application fit, not from a universal technology ranking.